Okay, let's talk a little bit about basic programming in C++ before we get into the topic of today's lecture, which is data. Okay, and I want to show you basically the smallest program that I can create. And I'm just going to run this. This is called a Hello World program. It just prints something to the screen. Okay, and then this is the program that allows us to do that. Okay, so at the top we have this #include iostream using namespace std. These are basically things that allow us to print to the screen. Okay, so we have this little black window. This is called the console window, and when we want to print to it, that's where the output's going to go. Then we talked about the flow of control always starting inside this thing called the main function. So we have a sequential flow of control from the top of main down to the bottom. Here we have this line that says cout, hello world, endl. Cout means basically print to the console window. Then we have hello world, and then endl means to end the line. And then all of our main functions will end with this return 0. And once the program reaches the very end of main, then that's when the program is complete. So all C++ programs are collections of functions. A function is just a named block of code. We use the curly braces to define the blocks of code. So here's a block of code with the name of main. All C++ programs must have a function called main. Main, like I said, is the starting point for the program. And the flow of control starts with the first line inside main and continues until the last line of main. By default, the flow of control, or the order that statements are executed, is from the top to the bottom. And like I said before, we're going to learn how to alter this flow of control in future lectures. For right now, our programs are going to be executed from the top of main to the bottom. Okay, so all running programs have a lifetime. A program is alive when we say the statements are being executed by the processor. Once all the statements have been executed, then the program is over, or it has died. Okay, so that's kind of our simplest program. When I run it, the program is alive for a little while, and then once I hit that button, the program ended. So let's talk a little bit about the C++ language. C++ has a syntax. The syntax is a collection of rules that define how C++ statements can be written. For example, all statements in C++ must end with a semicolon. If you leave one out, then you violated the syntax of the language. Okay, so here the statements are inside the function, and notice they all have this semicolon at the end. If I leave one out, notice I get this little red squiggly, just kind of like you'd see in a Microsoft Word document when you misspell something. This is your indication that you've done something wrong. You violated the syntax. And if you mouse over it, it says, well, there's an error. The compiler was expecting a semicolon, not on this line, but the line right above it. So I could put that back, and the little red squiggly goes away. Okay, English also has a syntax. So we could say something like this. The dog barks loudy. Okay, the rules of the English language say that you cannot have a period in the middle of the word. Okay. So here's a violation of the English syntax. And as far as I know, there's no word in the English language loudy. Okay, luckily the compiler will catch 100% of all syntax errors, and it will highlight them with the squiggles, and it'll give some kind of error message. Okay, the English language, though, also has semantics. And semantics have to do with the meaning of words. Okay, this violates no syntax rule, but there's an obvious semantic error. It's an error in the logic that we know to exist in the world. Right? Cats don't bark. Unfortunately, the compiler will not be able to catch any of the semantic errors we put in our code. So remember, the computer will do exactly what we tell it to do. For example, if I tell the computer to divide a number by 0, it will try and do that. Of course, even a computer, though, can't divide a number by 0, and attempting to do so will make the program crash and burn. This is a semantic error. The programmer must find all semantic errors, or error in programmer logic, and fix them. While learning to program, you're going to make many syntax and semantic errors. Until you've mastered the language, most of your time will be spent trying to find, identify, and fix your errors. And after you've mastered this language, you'll spend only slightly less time finding, identifying, and fixing errors. This is just what programming is about. Even the best programmers make a ridiculous number of mistakes. And I know because I think I've made just about all of them that can be made. Luckily, there are some great tools to help us figure out, what in the heck is going wrong with our broken code. There's a tool called a debugger that allows us to slow the program down. Remember, I mentioned programs run very, very fast. So it's good to be able to slow things down. And then the debugger also lets us look at what's inside of our memory. Okay, but I'll talk more about that later. Okay, let's talk about data. Manipulating data into usable information is the fundamental reason why people write computer programs. Okay, remember our black box. Our programs we can think of them like black boxes. We put something in and we get something out. Right? The box manipulates the inputs and transforms them into usable outputs. Okay, the data in our programs live in the computer's memory. Okay? And remember, I mentioned you can think of memory as this long series of boxes. So I'll draw this picture a lot in class, this idea of these boxes. Remember, memory is the only physical component that a programmer has to think about. While you're programming, you don't have to think about the processor or the hard drive or the I/O devices. The memory really is the only thing you have to actively think about. Now, every piece of data in a program has an address, a name, a value, and a type. Okay, so every piece of data lives in memory, or every piece of data that lives in memory has a physical address. Right, so all of these boxes, there's a numeric address assigned to each and every one of them. Okay, so this is the box with the physical address 1, this is the box with the physical address 2, and so on. If you have 8 gig of RAM, I mentioned this before, you have somewhere around 8 billion of these individual boxes. A little bit more than 8 billion actually, but this very last box will be somewhere will have the numeric value somewhere in the 8 billion range. Okay, so that's a lot of boxes. Luckily, we can also assign a name to a piece of data. Okay. So if programmers had to remember and work with addresses of data, it would be very hard for us to have any spare brain capacity to solve the actual problems our customers want us to solve. It would be very confusing to be dealing only with addresses. So luckily we can give a piece of data a name and use the name instead of the address. Right. So what we might be able to do is say, well, this box right here, we want to call this one largest number so far. Okay. And then in our program, whenever we want to refer to this box, we could just use this nice human-readable name, largest number so far. Okay. Every piece of data also has a value. I like to think of a piece of data as a box, and a value is what goes inside the box. Okay. So remember the largest value so far, I think, was the number 31. At some point we can put a value inside here, okay, inside this box. And then a programmer can always read what's inside the box and can write a new value in the box if they want to. However, as soon as a programmer writes a new value into the box, the old one is gone forever. That's just how memory works. So be careful when you assign a new value to a variable, because you'll never be able to get the old one back again. Okay, so I'm going to start to use this word variable to mean a piece of data. Okay, and we call data that can change a variable because obviously the value inside can vary or be changed. Okay, so remember, a variable is just a piece of data that lives in the computer's memory that has a name, okay, that programmers can refer to. We also said every piece of data has a type. Okay? And the type of a variable tells the computer how much memory is required for that box and what kind of values can be placed inside the box. Okay, different variables require different amounts of space and memory. If I was storing a human being's age, right, which might range only from 0 to maybe 100 or so, I would only need a small amount of memory to hold that number. However, if I was storing the entire first chapter of a book, I would need quite a few more boxes to store all the words in that chapter. So a data type tells the compiler how much room to set aside for each piece of data. There are some built-in types in C++, so I'm going to refer you to your textbooks for the complete list, but these are the most common ones. So the first one is called an integer, okay, or an int for short. And an int is just a whole number. Okay. Int is a keyword in C++, and examples of integers: 4 is an integer, 17 is an integer, -9 is an integer. Notice there's no decimal point in any of these numbers. That's because an integer cannot have a fractional part. It must be a whole number. A piece of data's type always defines the way that that piece of data can be manipulated. In other words, a piece of data's type defines what operations can be performed on it. So the operations that can be performed on an int are addition, subtraction, multiplication, and division. Okay? And we have symbols for these, of course. We have plus, minus, the star, and the / for division. Okay, when a programmer creates a variable of type int, it requires 4 bytes of memory. That's just how in C++ on a modern machine an int requires 4 bytes of memory. Okay, remember each byte is 8 bits, so 4 times 8, that's 32 bits of memory. Okay, what this means is that an int cannot hold an infinitely large number. There are a finite number of bits, in this case 32, that make up an int in memory. So it would be impossible to store an infinitely large number in a finite-sized box. Instead, an int has a range of valid values. The range of values that can be stored are somewhere around about -2 billion to about +2 billion. Okay, so here we have 0, and on the high end we have about 2 billion, and on this end we have about -2 billion. If you need a number bigger than this, you'll have to use a different data type, and there are some other options that we won't go into right now. Okay, a really surprising thing that happens though, when you go to the end of this number line and you add 1 to it, so remember we can always do arithmetic with these integers, what happens is it wraps around back to the negative numbers. Okay, so another way to think about this number line, here's 0, here's +2 billion, here's -2 billion. Okay. As you march your way through here, as soon as you cross this barrier, okay, so if you're at this very largest positive value and you add 1 to it, you immediately kind of cross over here and you get a negative number. Okay. So basically the number line is circular. when we deal with integers like this. Okay, and we have a name for this. Whenever you cross that barrier, that's called an overflow. Okay, and that almost always is some kind of error. Okay, so you could be multiplying two very large positive numbers together, and the computer could tell you that the result is negative, and that would certainly be unexpected. And unfortunately, we won't get any error messages or warnings when this happens, so you have to be careful to avoid these overflows. Okay, so ints again are used for whole numbers. Float are used. The float data type is used when you want a number that has a fractional part. Okay, so some examples of floats. 4.2, that's a float. 6.097, that's a float. Minus 1.21111. 6.0, that's a float. Okay, so the compiler distinguishes ints and floats by the presence or absence of the decimal point. So that decimal point is really important. Floats also happen to take up 4 bytes of memory, and therefore they have a finite range of values. The allowable operations on a float are almost the same as with ints. We have addition, subtraction, multiplication, and division. However, division with integers is a little bit different than division with floats. So with ints, when you take 5 divided by 2, integer 5 divided by integer 2, you might think you would get 2.5. Okay. However, the result of dividing two ints is always another int. Okay, but ints don't have a fractional part, so the 0.5 gets truncated or chopped off. And integer 5 divided by integer 2 is actually the integer value 2. Okay. With floats, when you divide, you get kind of the expected values. So float 5, that would be 5.0, divided by float 2, which is 2.0. This really will give you 2.5. Okay. And again, when you divide two floats, the result is always a float. So when you divide ints, you get an int. When you divide floats, you get a float. There's a special type of division that can happen with integers called modulus division. And a modulus division returns a remainder. So if we take integer 5 and do modulus division with integer 2, so integer 5, the percent sign is the symbol used for modulus division. Okay, what this means is, well, let's see, what is the remainder when we do this math? 2 goes into 5 2 times. 2 times 2 is 4. We subtract 1 and we get a remainder of 1. So 5 mod 2 is actually equal to 1. Okay, so mod is always a remainder. Regular division uses the forward slash symbol. Modulus division uses the percent sign. Okay, and regular division returns a quotient. Right, so remember 5 divided by 2 is equal to 2. Okay, that was returning the quotient with straight division. Modulus division returns the remainder. You might wonder why you would even want to do modulus division, but it actually comes in handy all the time. So in order to find out if an integer is even or odd, you could do a modulus divide by 2, and it turns out all even numbers will result in a 0, and all odd numbers will result in a 1. So for example, if we took 37 mod 2, okay, let's see, 2 goes into 37 18 times, and we'd be left with a remainder of 1. Let's look at maybe 38 mod 2. 2 goes in here 19 times. If we subtract, we get a remainder of 0. Okay. You can So you can see the even numbers have a value of 0, the odd numbers have 1. This is only 2 examples. I suggest you practice a few times and prove to yourself that that's really true. All even numbers mod 2 will be 0, all odd ones mod 2 will give you 1. In fact, let's practice right now. Let me put a few values on the whiteboard here, and then you can pause after I've written the equations out. Pause and work these out. So integer 10 divided by integer 2. Integer 1 divided by 2. Float 0.5 divided by float 0.5. 7 mod 3. 14 mod 2. 0 divided by 34. 1 mod 2. 8.4 minus 6.7. 4.5 mod 2.1. 3.0 divided by 0.0. 243 mod 12. And 243 divided by 12. Okay, so pause the video now and come up with a solution for each one of these values. And when you come back, I'll show you the answers. Okay, let's start with the first one, 10 divided by 2. Integer 10 divided by integer 2 is equal to the integer value 5. Integer 1 divided by integer 2 gives us the value 0. Okay, we know it's really 0.5, but the 0.5 part gets truncated, and integer 1 divided by integer 2 is 0. 0.5 divided by 0.5 is not integer 1, but floating 0.1. There is a difference. So 1.0, the computer treats different than just 1. 7 mod 3. Let's see, 3 goes into 7 2 times with a remainder of 1. After you do this a few times, you can start to do this in your head. 14 mod 2, I know that 2 goes into 14 exactly 7 times with a remainder of 0. So 14 mod 2 is 0. 0 divided by 34, 0 divided by anything, of course, is 0. 1 mod 2, let's see, 2 goes into 1 0 times. 0 times 2 is 0. We do the subtraction. Okay, 1 mod 2 is actually equal to 1. 8.4 minus 6.7. Okay, I think that's 1.7. Okay, 4.5 mod 2.1. That's kind of a trick. Okay, mod only works with integers, so this is a trick question. Another trick question: 3.0 divided by 0.0. Well, you can't divide by 0. Humans can't do it, computers can't do it, it doesn't make sense. So there's no value for that one either. 243 mod 12. Let's see, I think 12 goes into 243 20 times with a remainder of 3. So we have 3 there for the mod, and the quotient, 243 divided by 12, in this case would be 20. Okay, another peculiar problem with floats is that they rarely hold exact values. So for example, float 10 divided by float 3, well, you would think this is 3.3 repeating. Okay. However, that box has a certain size that can't hold an infinite number of 3's. Okay, and there really are an infinite number of 3's that come after that decimal point. But remember, each one of our pieces of data has a fixed number of bits. So it's impossible to put an infinite number of numbers inside a box that has a finite size. Pi is also a number that has an infinite sequence of digits, that don't repeat. The 3.3 repeating, at least we know they're all threes. Well, a number like pi, the digits don't repeat. So we can't really hold a true value of pi inside a variable either. Okay, we can hold numbers up to a certain degree of precision. So really, float 10 divided by float 3, the computer might store this as something like this. 3.3333332, which is very close to 3.3 repeating, but it is not exactly equal to 3.3 repeating. Okay, so those are the numeric types. There are also a couple types to hold text. So there's a data type called character, which is used to hold a single printable character. So for example, every key on the keyboard has a character equivalent. And a character is 1 byte. A character is really just an integer that maps to a certain character set. So in a C++ program, the ASCII character set maps numbers to printable characters. Okay, so let me try and make some sense of this here. So a character is really just a number. So the number 97, for example, maps to the lowercase letter a. And the number 98 maps to the lowercase b, and so on. Okay. What's unusual about characters is when a character is printed to the screen, the numeric value is converted into a character and the character is printed. So if we did a C out of 97, okay, we're not going to see the number 97. What we're going to see is the character that's associated with it, in this case an A. Okay, and I believe in the back of your book there is the ASCII character set that you can look at. I guess for now you just have to keep in mind a character really is just an integer value. Now a string is a collection of characters. So a single character by itself is not very useful, but if you can group characters together into this thing called a string, well then you can start to do some interesting things. So a string might hold a person's name or a description of a product for sale or the chapter of a book. Strings are interesting because the size of the box can grow or shrink to hold the exact number of characters that are in a string. So when you store a collection of text inside a string variable, it will make the box that holds it large enough to store all the characters inside. Okay, when I draw these boxes, though, I'm not going to try and make every box proportional to the number of bytes that are actually being used, just because it would make my drawing a little bit harder to do. I'm just going to draw a box and put values inside of them. However, keep in mind, different data types specify different sized boxes. Okay, let's talk about data declarations. So a data declaration is a command that tells the computer to do a few things. So when the flow of control gets to a data declaration, it tells the computer to carve out some unused group of bytes from your memory, mark them as being used, and then the program will give that box basically a name. After the variable has been created, a programmer can store a value inside that box or read a value from the box. Okay, a data declaration requires that you specify the data type and a name followed by a semicolon. This is the syntax. So the data type would be int or float or string, something like that. The name is some human readable name, something that makes sense, that describes that piece of data. And lastly, the semicolon is required to end all statements. Optionally, you can also assign an initial value to the box. So this creates a box and assigns a value to put inside that box. Names of variables there's a rule for that as well. Names of variables cannot include spaces or start with a number. You can only use the alphabetic characters or the numeric digits and the underscore. Okay, any other character is not allowed in the name of a variable. And if you try and put any of those other characters in there, you'll get a syntax error. So I always start my variable names with a lowercase letter and start each additional word with a capital letter. And we call this camel case because it kind of looks like a camel with the humps on its back. Okay, so in these examples I've written statements to hold an integer number of students. We need a whole number of students here because it doesn't make sense to have a fractional number of students. I can't have 2.3 students. I could either have 2 or 3, but not 2.3. Here I'm creating a float called height in feet, and this represents a person's height. So a value like 69.5 is valid. Here I'm declaring a variable called middle initial, whose type is character. And all character values are represented with single quotes. So you can put only at most one character inside single quotes and store that inside character. Okay, a string, like I said before, can hold multiple characters. All string values are represented in double quotes. Okay, so this says put the name Mark inside the box called name. When you create a variable, you don't have to specify an initial value, and if you don't, its value is undefined. This means that the value inside number of students, for example, it's a garbage value. There is a number in there, but I don't really know what it is. It might be 0, it might be something else. The programmer must assign a value to the variable before they use it in some arithmetic operation. Okay, so let's talk about assigning values to a variable. The value of a variable can be changed using this thing called an assignment statement. And assignment statements always move from the right to the left. Okay, so we take a value and we're going to stick it inside the box called, in this case, variable name. Okay, so here are some examples. Here we're putting the value 20 inside the variable called number of students. Here we're putting 72.78 inside the variable called height in feet. Here we're putting the character Q inside the box called middle initial, and here we're putting the name or the string John inside the variable called name. Okay, so remember we had this box called name, and it started out with my name in it. But when we store a value inside the box, when we say, the way I read this is, we want to store John inside the variable called name. Okay, this means take the string John, and again, kind of assign it to the variable called name, and Mark will go away forever. So let me erase that. Okay, and now if we were to look inside this box called name, we would see the value John. Okay, so the old value is gone forever whenever you assign a new value to a variable. Whenever there's a name of a variable in code, the computer goes and either gets or sets the value. Okay, so one thing I could do, I could create another variable. Let's say I had an int called num in room. This is supposed to represent the number of people in a room. And I can set it equal to number of students plus 1. Okay, and what this is going to do, Okay, when the flow of control gets here, there are actually a few things going on in this one line. When the flow of control gets here, this says go carve out room for this box called num in room. Okay, so that happens first. Okay, now the computer wants to store a value inside there, right? Because this is an assignment statement. We want to put a value inside the box. But in order to do that, it has to do a little bit of arithmetic first. So the number of students, let's say it has the value 20. So again, there's going to be a box with that name. And based on that last set of assignment statements, the value 20 is going to be inside there. So now, whenever in code you refer to the name of a variable, you kind of think of the computer as going and finding the contents of that variable. In this case, it's 20. And then we're going to add 1 to that. 20 plus 1 is 21. Only after we do that arithmetic are we going to store the value 21 inside the box called num in room. Okay, so again, first the computer grabs the value inside number of students. Next it adds 1 to that value. Okay, so the one extra person is supposed to be the professor. Finally, it assigns the result of the arithmetic to the variable called num in room. Okay, this is a really important point. The flow of control must reach the declaration of a variable before you can start assigning values to it. Okay. Before the data declaration happens, the variable is actually not in memory. Only after the declaration has been executed has room been set aside in memory and a name given to that variable. Okay, so if we did something like this, this would be a mistake. Let me copy some of this code here. And paste it here. So notice the order that I'm doing things here. Here I remember the flow of control is going to go from the top of main to the bottom. And I'm trying to assign the value 40 to this variable called age. But notice the flow of control has not gotten to the declaration of age. And this is why we get the syntax error. It says identifier age is undefined. That's because the compiler is trying to compile this from the top down. And when it gets right here, it's not smart enough to look forward and see that the declaration is on the very next line. Okay, the declaration must come first. So in order to make this work, we have to declare the variable first. This is when age will actually be carved out in memory, and only after that can we assign a value to that variable. Okay, so that's really important. You have to declare a piece of data before you can start using it. Okay, this would also be a mistake if we left the declaration out altogether. Okay, for basically exactly the same reason. The compiler doesn't know what age is. We haven't told it the type, so it doesn't know if this is a valid thing to do. You know, if this were a string, it wouldn't make sense to put the number 40 inside a string. Okay, so we must include the declaration of a piece of data before we can use it. And luckily, the compiler will catch these types of errors and give us a squiggly. And almost before we even finish the line, we'll know that we did something wrong. In the old days, you actually had to, compile your program and see this list of error messages before you knew anything bad happened. All right. Okay, we've just seen that the computer evaluates arithmetic expressions using variables and values. So remember, the name of a variable, the whenever the flow of control is on a line with the name of a variable, that that name is basically replaced with the value inside the variable. Now these arithmetic expressions can be quite complex. So there's an order of operations that the arithmetic operations take place in. So this is pretty similar to how any math textbook would be. The multiplication and division operations have a higher precedence than addition and subtraction. Now a programmer can force a different order using parentheses. And I think it's a good idea to use parentheses pretty much all the time. It does make your code quite a bit easier to read. So if we look at this expression, 3 minus 2 times 6, the multiplication will happen first, and this will really be 3 minus 12, which of course is minus 9. Here, 10 divided by 5 is 2. 2 plus 3 is 5. Here we have 3 minus 1 times 3 plus 2, but without the parentheses, the multiplication would happen first. So this is really 3 minus 3 plus 2, or 2. This one's a little bit tricky here. We have parentheses, so that's going to happen first. 4 minus 2 is 2. Then we'll just go left to right because we have basically two divisions, a mod division and a straight division. 13 mod 7 is 6. 6 divided by 2 is 3. So the result of this one would be 3. This one's really complicated. We have nested parentheses. But we just do the innermost one first. 4 minus 1 is 3. 3 times 2 is 6. 6 plus 23 is 29. Okay, so this this whole thing results in the value 29. Then we have this mod division followed by the addition here of 10 plus 6 is 16. So it would be 29 mod 16, I think, is 13. That would be the result of this value, or this expression here. And then this is kind of an interesting one because we're mixing floats and ints. So 5 divided by 2.5 is 2.5. Or I'm sorry, it's actually 2.0. Plus 7 divided by 3 is integer 7 divided by integer 3 is 2. Okay, so 2 plus 2 is 4, minus 1 is we would think would be 3. Actually, let me write this one out. Okay, so 5.0 divided by 2.5 plus 7 divided by 3 minus 1. Okay, so if we were to rewrite this, looking at the innermost set of parentheses first, 7 divided by 3 is actually integer 2. Okay, 5.0 divided by 2.5 is 2.0. Okay, and this is where we have the mix of ints and floats. And the rule is the compiler will always change the integers to floats. So this will actually be turned into 2.0 plus 2.0 minus 1.0. So 2 plus 2 is 4. 4 minus 1 is 3.0. Okay, so the compiler will always force your ints into floats when they're mixed. And there's a reason for this. You don't lose any information when you turn integer 1 into, if you transform that into floating point 1.0. Okay, the reverse is not true. If you had a floating point 2.3 and you wanted to turn that into an int, it would chop off the fractional part and you'd lose some of that data. So it's safer to cast from int to a float. And the compiler does this implicitly. This is called an implicit cast, whenever you mix integers and floats together. Now you, the programmer, can temporarily change the value of an int or a float using something called an explicit cast. So that looks something like this. Okay, this says temporarily take integer 3 and turn it into 3.0. And then temporarily take this value 2 and turn it into 2.0. And then the result will be 1.5. So even though we're using ints here, there's no decimal point, our explicit cast just says, just for the lifetime of this statement, this one statement, temporarily turn this number into 3.0 and this one into 2.0, then do the math, and we'll be left with, again, a floating point number. Okay, just a couple other things here. So you might have noticed some stuff that shows up in green in my code. Those are called comments. Okay, and comments are a way for a programmer to write a note to either oneself or other programmers. And comments are totally ignored by the compiler. Okay, so there's two types of comments you can put in a C++ program. This is called a single line comment. So anytime there's two slashes, anything till the end of the line will be ignored by the compiler. And this is called a multi-line comment. So this slash star will make everything a comment until there's a star slash. So if you have a really long comment, you can kind of wrap it in these multi-line comments. And then just one other note about the stuff that goes in the top of every single program. Okay, so I mentioned this pound include IOStream using namespace std. This is basically boilerplate stuff that should be in every single program that you write, because these allow us to print to the screen and also read from the keyboard. So a pound include is just a way to import some existing code into your program. So when you pound include IOStream, that allows you to read from the keyboard and write to the monitor. And we'll talk a little bit more about that in the next lecture. This basically will happen every single time we write a program in this class. So I would just kind of start to create a template for your code files. That would look something like this. Okay. So every single program needs these things. You need the IOStream, you need a main. The main needs to return 0. Okay, so all your programs will basically start out looking like this, and then you'll add things to it. You should also pound include string whenever you're going to use the string data type. So maybe you'd want to add this to your boilerplate code. Okay, all the other types, int, float, character, those are built into the language. The string data type was added late in the creation of C++, so it lives in a separate library. Okay, so whenever you're going to use a string, which is going to be in just about every program, you want to make sure you also pound include string at the top. This using namespace std, for now, just always include this. It holds a definition of some things that we'll use in every single program. And I'll come back and mention it more later on. But for now, let's just you do need it, but I'm not going to kind of explain it in too much detail. Let me show you one more program, and then we'll end this lecture. So this does this one program. There's a lot of things we talked about in this lecture. So primarily creating variables and assigning values and manipulating these values. Okay, so we have our main function. That's where the program's going to start. And the very first thing we do is we declare some variables that we're going to use in the program. So we're going to have a string for the first name, a string for the last name, an int for the age. I'm going to calculate an age in the future, so I have another integer called future age. I have a float for the height, and another float to find the height divided by 2, basically. Okay, so when the flow control reaches here, we're actually creating boxes, right? So every single time the flow of control reaches the declaration of a variable, we could think of it as going and carving out a little chunk of space. Right, so there was a variable called first, which was a string. We had a variable called last. Okay. So anything that doesn't have a name under it, we can consider that free and usable memory. Right, we had a variable called age, future age, height. Okay. So every single time the flow of control reaches one of these points, it goes and makes room for these variables. Next, we assign some values to the variables. So we store my first and last name in there, my age in 10 years. Again, notice whenever you refer to the name of a variable, you can kind of think of it as being replaced by the value that's inside that variable. So 40 plus 10 will be 50. That's what's going to go inside future age. This is my height with my shoes on. And if I take the height divided by 2, that should chop that in half and store that inside the half height. And then down here, I'm going to display the results. So I'm going to see out, I'm going to print my first name, my age, how old I'm going to be in 10 years, my height, and half my height would be this size. Okay, so I'm going to run this. And we should see Mark Mahoney's age is 40, in 10 years you'll be 50. Your height is 70.5 inches. Half your height is 35.25 inches. Okay, so we've created some variables, we've filled and manipulated the variables, and then we display the results. It's a pretty typical program. Okay, you declare variables, you gather some input, you do some processing, you display the output.